Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, the Taylor and Maclaurin series, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view the 3 videos titled Properties of Infinite series prior to watching this video. In this video, we will be discussing the definition of the Taylor and Maclaurin series, the Taylor and Maclaurin series theorem, convergence of these series, Taylor and Maclaurin series as a function, and using these series to approximate another function. The Taylor series of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. If 0 is the point where the derivatives are considered, the Taylor series is also called a Maclaurin series. The theorem for the Taylor and Maclaurin series states, suppose f is a function that has derivatives of all orders on an open interval c minus r and c plus r for r greater than 0. If f can be represented by the power series, the sum from k equals 0 to infinity of a sub k times the quantity of x minus c to the k power, whose radius of convergence is r, then f of x equals f of c plus f prime of c times the quantity of x minus c plus the second derivative of f at c over 2 factorial times the quantity of x minus c squared plus the third derivative of f at c over 3 factorial times the quantity of x minus c cubed, and so on, including the nth derivative of f of c over n factorial times the quantity of x minus c to the n power, and on to infinity. Please note that the first term, f of c, omits an x minus c because it is taken to the 0 power equaling 1, and also omits the denominator 0 factorial because it too is equal to 1. Likewise, the second term omits the denominator 1 factorial because it equals 1. The sum from k equals 0 to infinity of the kth derivative of f at c over k factorial times the quantity of x minus c to the power of k is called the Taylor series. When c equals 0, then the sum from k equals 0 to infinity of the k derivative of f of 0 over k factorial times x to the k is called the Maclaurin series. For example, let's express f of x is equal to e to the x as a Taylor series at c equals 0. By definition, this is also a Maclaurin series. For reference's sake, we'll write the Maclaurin series form, then list the first 3 derivatives of e to the x, each of which is e to the x. Then we take f of c, which in this case is f of 0, which in each case equals 1. Therefore, e to the x equals the first term of the series where k equals 0, 1 over 0 factorial times x to the 0, which equals 1, plus the second term where k equals 1, or 1 over 1 factorial times x to the first, which equals x, plus the third term where k equals 2, 1 over 2 factorial times x squared, which equals 1/2 x squared, plus the fourth term where k equals 3, or 1 over 3 factorial times x cubed, which equals 1 over 6 times x cubed, and so on, including the nth term, 1 over n factorial times x to the n. This Maclaurin series is then expressed as a sum from k equals 0 to infinity of x to the k over k factorial. Next, we determine the convergence of the same series. For this, we can use the ratio test. Remember the ratio test from a previous video. It states that the limit, as n goes to infinity, of the absolute value of a sub n plus 1 over the absolute value of a sub n equals L. If L is less than 1, then the series converges absolutely. If L is greater than 1, then the series diverges. If L is equal to 1, then the test provides no information about convergence or divergence. In this case, we take the limit, as n goes to infinity, of the absolute value of x to the n plus 1 over n plus 1 factorial, all over x to the n over n factorial. First, we simplify the compound fraction. Then x to the n plus 1 equals x times x to the n. And n plus 1 factorial is equal to n plus 1 times n factorial. Next, the x to the n and the n factorials cancel, leaving us with the limit as n goes to infinity of the absolute value of x over the absolute value of n plus 1, which is 0 for all x's. This means the series converges for all x's, and the interval of convergence is from negative infinity to infinity. In this next example, let's find the Taylor series for f of x equal to 1 over x at c equals 1. Again, we will start with the Taylor series format, then take the derivatives. With f of x equal to 1 over x, f of 1 equals 1. The first derivative of 1 over x is negative 1 over x squared. The first derivative of f at 1 will then be negative 1. The second derivative of f is 2 over x cubed, making the second derivative at 1 equal to 2. The third derivative of f is negative 6 over x to the fourth, making the third derivative of f at 1 equal to negative 6. The fourth derivative of f will then be 24 over x to the fifth, making the fourth derivative of f at 1 equal to 24. Putting together the series for the first 5 terms gives us 1 over 0 factorial times the quantity of x minus 1 to the 0 power, minus 1 over 1 factorial times the quantity of x minus 1 to the first power, plus 2 over 2 factorial times the quantity of x minus 1 squared, minus 6 over 3 factorial times the quantity of x minus 1 to the third power, plus 24 over 4 factorial times the quantity of x minus 1 to the fourth power. This simplifies to 1 minus the quantity of x minus 1, plus the quantity of x minus 1 squared, minus the quantity of x minus 1 cubed, plus the quantity of x minus 1 to the fourth power. This series can be expressed as a sum from k equals 0 to infinity of negative 1 to the k times x minus 1 to the k power. With the Taylor series now established, we can determine an interval of convergence for this series. For this, we will again use the ratio test, which states that if the absolute value of a sub n plus 1 over the absolute value of a sub n is less than 1, then the series converges absolutely. For this series, the ratio test will be negative 1 to the n plus 1 times the quantity of x minus 1 to the n plus 1 over negative 1 to the n times the quantity of x minus 1 to the n. This simplifies the absolute value of x minus 1. Therefore, this series converges when the absolute value of x minus 1 is less than 1. We next solve the absolute value by splitting it into the two equations x minus 1 is less than 1 and x minus 1 is greater than negative 1. From this, we can construct the compound inequality negative 1 is less than x minus 1 is less than 1. Add 1 to the center to cancel the minus 1, then also add it to both sides to get 0 is less than x is less than 2. This means the series converges on the interval described by the compound inequality 0 is less than x is less than 2. We then verify the endpoints. So we look at the series when x equals 0. Replacing x with 0 in the series results in the sum from k equals 0 to infinity of negative 1 to the power of 2k, which equals the infinite sum of 1. This sum diverges because the partial sums do not approach any finite limit. Doing the same thing for x equals 2 gives us a sum from k equals 0 to infinity of negative 1 to the k power. This sum diverges because the partial sum also does not approach a finite limit. Therefore, the interval of convergence is from 0 to 2. For the next example, let's find the Taylor expansion for the polynomial f of x is equal to 3x cubed plus 2x squared plus 5x minus 6 around c equals 1. First of all, f of 1 is equal to 4. The first derivative of the function is 9x squared plus 4x plus 5, making the first derivative of the function at 1 equal to 18. The second derivative of the function is 18x plus 4, making the second derivative of the function at 1 equal to 22. The third derivative will be 18. Every other subsequent derivative will be 0. Putting together the series gives us 4 over 0 factorial times the quantity of x minus 1 to the 0 power, plus 18 over 1 factorial times the quantity of x minus 1 to the first power, plus 22 over 2 factorial times the quantity of x minus 1 squared, plus 18 over 3 factorial times x minus 1 cubed. The series will end there as all of the subsequent terms will be 0. We first simplify 4 over 0 factorial is 4 over 1, or 4. 18 over 1 factorial equals 18. 22 over 2 factorial equals 11. And 18 over 3 factorial equals 18 over 6, or 3. Next, we complete the arithmetic within the parentheses. 18 times the quantity of x minus 1 equals 18x minus 18. X minus 1 quantity squared equals x squared minus 2x plus 1. And x minus 1 quantity cubed equals x cubed minus 3x squared plus 3x minus 1. Next, we distribute, then combine like terms. 4 plus 18x minus 18 plus 11x squared minus 22x plus 11 plus 3x cubed minus 9x squared plus 9x minus 3. We continue combining like terms to get the final polynomial 3x cubed plus 2x squared plus 5x minus 6. Just as in this example, the Taylor series of any polynomial is the polynomial itself. Next, let's find the Maclaurin series for f of x is equal to sine x. Sine 0 equals 0. The derivative of sine is cosine. Cosine 0 is 1. The second derivative is negative sine. Negative sine of 0 is 0. The third derivative is negative cosine. Negative cosine of 0 is negative 1. The fourth derivative is sine, and sine 0 equals 0. Therefore, sine x equals f of 0 plus f prime of 0 over 1 factorial times x, plus the second derivative of f at 0 over 2 factorial times x squared, plus the third derivative of f at 0 over 3 factorial times x cubed, plus the fourth derivative of f at 0 over 4 factorial times x to the fourth. F of 0, the second derivative of f at 0, and the fourth derivative of f at 0 all equal 0 and may be removed from the series. Filling in our known values, we get sine x equals x minus x to the third over 3 factorial. We can then project the next two non-zero terms to be x to the fifth over 5 factorial minus x to the seventh over 7 factorial. This will give us a sum from k equals 0 to infinity of negative 1 to the k times x to the power of 2k plus 1 over 2k plus 1 factorial. Next, let's find the Maclaurin series for cosine of x. For this, we'll start with the series from the previous example. Sine x equals x minus x cubed over 3 factorial, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial. Since the derivative of sine x is cosine of x, we will take the derivative of both sides of this equality to get cosine x is equal to 1 minus x squared over 2 factorial, plus x to the fourth over 4 factorial, minus x to the sixth over 6 factorial. Therefore, the series can be expressed as cosine of x equals the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k over 2k factorial. Using a Taylor or Maclaurin series is one way of approximating the value of a function. For example, cosine x equals the sum from k equals 0 to infinity of negative 1 to the k times x to the 2k over 2k factorial, which equals 1 minus x squared over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, and so on. The next term in the series would be x to the 8th over 8 factorial. Let's next evaluate the function f at pi over 90. Using the first four non-zero terms in the series, we get 1 minus 1/2 times pi over 90 squared, plus 1 over 4 factorial times pi over 90 to the 4th, minus 1 over 6 factorial times pi over 90 to the 6th, which equals approximately 0.9994. Since this is an alternating series, this approximation has an error given by the next term in the series, or the absolute value of 1 over 8 factorial times pi over 90 to the 8th power, which is approximately equal to 5.47 times 10 to the negative 17th power. We can now use the Taylor or Maclaurin series to evaluate an operation that would be difficult to calculate using other means. For example, the integral from 0 to 1 of sine of x squared dx. Previously, we calculated sine x as equal to the sum from k equals 0 to infinity of negative 1 to the k times x to the power of 2k plus 1 over 2k plus 1 factorial. Next, by squaring x, we get that sine of x squared equals the same series except x squared, which means the sum from k equals 0 to infinity of negative 1 to the k times x to the 4k plus 2 over 2k plus 1 factorial. This sum will be sine x squared equals x squared over 1 factorial minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial, and so on. The integral of the first four terms in this series can be more easily taken than the integral of sine x squared. For this step, we will also work out the factorials for easier arithmetic. The integral will be x to the 3rd over 3 minus x to the 7th over 42 plus x to the 11th over 1320 minus x to the 15th over 75,600 evaluated from 0 to 1. This gives us approximately 1 cubed over 3 minus 1 to the 7th over 42 plus 1 to the 11th over 1320 minus 1 to the 15th over 75,600 minus the quantity of the same terms using 0, which can all be removed. This gives us 1/3 minus 1 over 42 plus 1 over 1320 minus 1 over 75,600. We then calculate the least common denominator to be 831,600. Applying this to each term, we get 277,200 minus 19,800 plus 630 minus 11 all over this denominator. This equals 258,019 over 831,600, which equals our final answer of approximately 0.310 taken to 3 decimal places. For our last example, we will find the Taylor polynomial for f of x is equal to ln of x squared at c equals 1. I will start by simplifying ln x squared to 2 ln x and then take 4 derivatives. 2 ln 1 equals 0. The first derivative is 2 over x, making the first derivative at 1 equal to 2. The second derivative is negative 2 over x squared. At 1 would be negative 2. The third derivative is 4 over x cubed, making the third derivative at 1 equal to 4. The fourth derivative is negative 12 over x to the 4th, and at 1 would be negative 12. Using the Taylor series format as a guide, the Taylor series for ln of x squared equals 0 over 0 factorial times the quantity of x minus 1 to the 0 power, plus 2 over 1 factorial times the quantity of x minus 1 to the first power, minus 2 over 2 factorial times the quantity of x minus 1 squared, plus 4 over 3 factorial times the quantity of x minus 1 cubed, minus 12 over 4 factorial times the quantity of x minus 1 to the 4th. The first term is 0. Simplifying the rest gives us 2 times the quantity of x minus 1 minus the quantity of x minus 1 squared plus 2 over 3 times the quantity of x minus 1 to the third minus 1/2 the quantity of x minus 1 to the fourth power. To check the accuracy of our Taylor series, let's use it to compute for f of 1.1, which is approximately 0.1906204. We replace x in our polynomial with 1.1 to get 2 times the quantity of 1.1 minus 1, minus the quantity of 1.1 minus 1 squared, plus 2 over 3 times the quantity of 1.1 minus 1 cubed, minus 1/2 times the quantity of 1.1 minus 1 to the fourth. This simplifies to 2 times 0.1 minus 0.1 squared plus 2 over 3 times 0.1 cubed minus 1/2 0.1 to the fourth. We simplify again to get a Taylor polynomial in 4 non-zero terms equal to 0.2 minus 0.01 plus 0.002 over 3 minus 0.0001 over 2, or approximately 0.1906167. If we have done our work correctly, then taking a fifth derivative will give us a more accurate answer. The fifth derivative of x is 48 over x to the fifth, making the fifth derivative at 1 equal to 48. We then add the term 48 over 5 factorial times the quantity of x minus 1 to the fifth power to our series. This term simplifies to 2 over 5 times x minus 1 to the fifth. Applying this term to f of 1.1 gives us 2 over 5 times 1.1 minus 1 to the fifth, or 2 over 5 times 0.1 to the fifth. We can now calculate our series of 5 non-zero terms, adding 0.00002 over 5 to the previous 4-term calculation to get 0.1906207, which is an approximation closer to the actual answer. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the academic support coordinator on your respective campus. Thank you, and good luck with your studies.